What we're going to talk about today are something called random variables, and we're going to talk about discrete and continuous random variables. And I want you to look at this first problem. If we roll a fair die, the possible outcomes are the numbers 1 through 6. Each of these numbers has a probability of 1 out of 6. Rolling a die is a probability experiment whose outcomes are numbers. The outcome of such an experiment is called a random variable. And what a random variable is it's a numerical outcome of a probability experiment. And it's usually denoted by capital letters. And what I want to talk about first is something we've already talked about in this course, and that's discrete and continuous. And this time it's going to be discrete and continuous random variables. Just like before, discrete is something that I can count. And what a discrete random variable is they're random variables whose possible values can be listed or counted. Examples include the numbers that come up when you roll the die. Like what we've talked about in class, the number of siblings that you have. Something that I could list or I could count. When we're talking about these discrete random variables, they may be infinite. And you all know infinite means goes on forever, doesn't end. We do not cover infinite ones in this course, but an example of an infinite one would be the list of all whole numbers. And what I want to talk about next will be continuous random variables. Same as before, continuous is going to be something that you measure. And they're random variables that can take on any value in an interval. Examples include height of a student, the amount of electricity that you use, and what we're going to focus on in this chapter will be discrete. And I want to talk about a probability distribution for a discrete random variable, something that I can list or something that I can count. What a probability distribution is. A probability distribution for a discrete random variable specifies the probability for each possible value of the random variable. If you look down here, it's going to look like this. And we'll talk more about this one in a minute, but it's going to look like a table like that, a chart. And here's what the properties are. All of the probabilities, and we talked about this in chapter 5, all of the probabilities must be between 0 and 1. To write that out mathematically, you could write it like this. 0 is less than or equal to P of X, which is less than or equal to 1. And also, if you look at the probabilities, all of your probabilities must sum to 1. And mathematically, that would look like this. The sum of my probabilities has to equal 1. And I want you to look at this problem. It says, a fair coin is tossed twice. Let X be the number of heads that come up. Find the probability distribution of X. So here's what it's going to look like. X is my number of heads, and I want to know what P of X is. And before I can get this, I need to figure out what are my possible outcomes if I toss a coin twice. And here's what I might get. I might get 2 heads, okay? Or I might get 2 tails. Or I might get heads, tails, or I might get tails heads. And there are no other possibilities that I could get. So the number of heads I could get would be 0, 1, or 2. So I'm going to go down here and I'm going to list 0, 1, or 2. And the chance that I get 0 heads would be that. So my chance of 0 heads would be 1 out of 4 or 0.25. You don't have to do the fractions and the decimals. That's redundant. I'm just showing you on this one both ways. Most of the time we use decimals. The chance of getting 1 head would be 1, 2. So 2 out of 4 or 0.5, 0.50. And the chance of getting 2 heads would be right there, 1 out of 4 or 0.25. And if you look at them, 1/4 plus 2/4 plus 1/4 is 2, 3, 4/4, which is 1. 0.25 plus 0.50 plus 0.25 is 1. They have to sum to 1, and they have to be between 0 and 1. Now, if you look at this next one, and I want to know if it is a probability distribution, and the answer to this is no, because your probability can't be negative. All right, so I'm going to say this. I'm going to say no. The probability of 3, and you could say is negative would be fine, but I'm going to say the probability of 3 is not between 0 and 1. So that is not a probability distribution. When you look at this one, it's asking the same thing. Is this a probability distribution? And I want you to look at that first look at the x's. And note that this x is negative, but that is perfectly fine. Okay, so x can be negative. I'll show you some in a minute where it is negative. And I'm going to look at the probabilities. They all look good. Take your calculator and add them and pause the video. Make sure they sum to 1. And here's what I found. Yes, all probabilities are between 0 and 1. And they sum to 1. The second one, decide if the following is a probability distribution. Right there, I can tell that it's not. P of 1 is not between 0 and 1. And when you look at this next one, it says 4 patients have made appointments to have their blood pressure checked at a clinic. Let X be the number of them that have high blood pressure. The probability distribution of X is as follows. When it tells you it's a probability distribution, you do not have to check it. All right, so here's what I'm going to do. First one, I want the probability that I have 2 or 3 patients with high blood pressure. 2 and 3 are mutually exclusive. I can't have 2 and 3 at the same time. Doesn't make sense. It's mutually exclusive, so I can add them. So all I'm going to do is do P of 2 plus P of 3. And I get 0.27 plus 0.08, which is 0.35. Notice how in the probability distribution, the x's are all in order. You want them to go in order because that helps you with a problem like we're doing right now. All right, when you look at B, and I want the probability that's more than 1. Remember, like Chevy Chevs, it was at least 75%. Watch your words with this. If it says more than 1, I'm going to start at 2. Okay, so I'm going to start at 2. And I'm going to say, okay, I want the probability of, I'm going to write this one a little different. You can write either way you want. 2 or 3 or 4. I'm going to add all of these. All right, so I'm going to have 0.27 plus 0.08 plus 0.01, which is 0.36. And the last one, I want the probability of at least 1. That's everything we had in B, plus at least 1 starts at 1. All right, so it's going to be P of 1 plus P of 2 plus P of 3 plus P of 4. So 0.41 plus 0.27 plus 0.08 plus 0.01, which is going to be 0.77. And an easier way to do that using the complement rule from what we talked about in chapter 5, if you use the complement rule, all the probabilities have to sum to 1. Okay, so everything sums to 1. I want everything but probability of 0. If I do 1 minus 0.23, I also get 0.77. And sometimes the complement rule is a little bit easier. It just depends on the problem. It depends on the situation. We're going to skip this. Check your understanding. I want you to pause the video and do the next two. And I will pause my video and turn it back on and explain it. But pause it until you try it. When you look at the top 3, they all look good as far as the P of X's being between 0 and 1. So they're fine. The first one, when you add them, you will see that they add to 1. So this one's good. The second one, the same thing. When I add them, they add to 1. The third one, when I add these, they do not add to 1. So that's no. When you look at this next one, I want the probability that a student participates in exactly 2. So all I want is 0.45. More than 2, I want 3 or 4. And you don't have to write all the work out. You can see what I'm doing this time. Just write your numbers that you're adding. And I'm going to get 0.35. And the next one, it says I want at least 1. And I'm going to do this by the complement rule. So when I want at least 1, I want 1, 2, 3, 4. I don't want 0. So I'm going to do 1 minus the probability of 0. Or 1 minus 0.06 or 0.94. The next thing we're going to do is I want to talk about probability distributions and populations. And it says statisticians are interested in studying samples drawn from populations. We're going to spend most of our course talking about this. Random variables are important because when an item is drawn from a population, the value observed is the value of a random variable. The probability distribution of the random variable tells how frequently we can expect each of the possible values of the random variable to turn up in the sample. And I want you to look at this problem. It's talking about a parking facility. And I've got 1,000 parking spaces. And like I think of BWI, even though BWI would be much bigger than this. If you look at this covered long term, pretend I've got a hat and I've got 142 $2 tags in this hat. Okay, so 142 of them. I've got 378 $4.50. And then I'm going to, etc. And then I'm going to randomly draw one. And it says the parking space is selected at random. Let X represent the hourly parking fee. And I want the distribution of X. And like I told you, you want to go least to greatest. So my least money would be $1.50. Then I could draw a $2 spot, or a $4 spot, or a $4.50 spot. And then I just figure out the probabilities. So the probability that I draw a 150 spot is 423 over 1,000, right? Because I've got 1,000 parking spots. If you type that in on your calculator, it's 0.423. The probability of $2 is 142 over 1,000. Same thing as 0.142. The probability of $4 is 57 over 1,000. This is not 0.57, it's 0.057. You move the decimal 3 places to the left. And the probability of 450 is 378 over 1,000, or 0.378. Take a minute and add your P of X's and make sure that they sum to 1. That's a check for yourself to make sure that you did them correctly. We did not do this one in class. We might come back to it next week. We will just skip that one for right now. But I want you to look at this one. It says probability distributions can be represented with histograms to visualize the distribution. The following presents a probability distribution and histogram for the number of boys in a family of 5 children, using the assumption that boys and girls are equally likely and that births are independent. Here's a table, and here's the histogram. I like the histogram better because you can see it better. It's a visual interpretation. Notice that when it's a discrete random variable like 0, your whole bar there is 0, this bar is 1, this bar is 2, and so forth. Okay? And I want you to pause the video and try this problem down here. And then we'll come back to it and check your answers. This one says, what's the probability that a randomly chosen woman has exactly 2 children? All right, so that's going to be 0.244. What's the probability that a randomly chosen woman has fewer than 2? So fewer than 2 would be 1 or 0. So I'm going to add 0.273 plus 0.16, and I'm going to get 0.433. What's the probability that a randomly chosen woman has either 4 or 5 children? Come down here and just add your 4 or your 5. 0.082 plus 0.039, 0.121. And what I want to talk about next is the mean of a discrete random variable. The mean is always a measure of center. The mean of a random variable provides a measure of center for the probability distribution of the random variable. Another name for the mean of a random variable is the expected value. And what the formula is for finding the mean, and I'm going to tell you what you do first, then I'll give you the formula. What you're going to do is multiply every value by its probability. Then you're going to add the products. What it looks like in a formula sheet, it looks like this. And it's called mu of x. And what it is the sum of x times p of x. It's also known as expected value. Mu of x equals e of x. They mean the same thing. Your text uses expected value a lot when they're talking about money. It's kind of like when we were doing the weighted means, right? So let's look at this problem. It says a computer monitor is composed of a very large number of points of light called pixels. It's not uncommon for a few of these pixels to be defective. Let x represent the number of defective pixels on a randomly chosen monitor. The probability distribution of x is as follows. You don't have to check it. It's telling you that. And I want the mean number of defective pixels. So what I want is mu of x. And what I'm going to do, I'm going to take my x value times my p of x. I'm going to take my x value times p of x. X times p of x. X times p of x. And like I said, it's like what we did with weighted means. I have a higher chance of getting a 1, so it needs to carry more weight. It does where I did 1 times 0.5. Take your calculator and add that. And what you're going to get is mu of x is, and pause the video if you need to, but mu of x is 1.2 or e of x is 1.2. You are not going to round these. And what that means, obviously the computer person is not going to go in and find 1.2 pixels, but in the long run, after many computers, they're going to expect an average of 1.2. If they wrote down their whole life the number of defective pixels and averaged it out, it's going to approach 1.2. And let's talk about that a little bit more mathematically. If a probability experiment that produces the value of a random variable is repeated over and over, the average of the values produced will approach the mean of the random variable. When the probability experiment is sampling from a population, our interpretation of the mean says that as the sample size increases, the sample mean will approach the population mean. This is known as the law of large numbers for mean. So what that's saying is if we sample items from a population, like those computers, as the sample size grows larger, the sample mean will approach the population mean. The more computers you sample, the closer your average is going to be to 1.2. This next problem, it says there are many occasions in which people want to predict how much they're likely to gain or lose if they make certain decisions or take a certain actions, like the stocks. Often this is done by computing the mean of a random variable. In such situations, the mean is sometimes called the expected value and is denoted by E of x. We've already talked about it. If the expected value is positive, it's a gain. If it's negative, it's a loss. If it's zero, you're going to break even. And look at this problem. It says a mineral economist estimated that a particular venture had a probability of 0.4 of a $30 million loss, 0.5 of a $20 million profit, and 0.1 of a $40 million profit. Let X represent the profit. If you make a table of this, it's real easy to do. And like this one gives you a hint. It says find the probability distribution of the profit and the expected value. And then you want to know, is it an expected gain or an expected loss? So here's what I'm going to do. X and P of X. Now, worst case, we can lose 30 million. So negative 30. Remember I told you X could be negative. There's a 40% chance of that. $20 million profit, there's a 50% chance of that. $40 million profit, there's a 10% chance of that. And what we're going to do is just find mu of X or E of X. Both things meet the same. And I'm going to do the same thing. I'm going to take X times P of X plus X times P of X plus X times P of X. When you type this, I would type it on your calculator just like that with the parentheses. Pause the video and type it. And once you type it, you should get mu of X equals 2, okay? Or E of X equals 2. You don't have to use both notations. Where it's positive, it's an expected gain. And then it's an expected gain of 2 million. And what that means, like, if many people invested in this, on average, they're going to experience a gain of 2 million. What happens in the short run? Anything can happen. It's not going to be 2 million, right? For you, you're going to lose 30 or gain 20 or gain 40. On this one, it says an insurance company sells a 1-year term life insurance policy to a 70-year-old man. The man pays $400. If he dies within 1 year, the company will pay $10,000 to his beneficiary. The probability that a 70-year-old man is still alive 1 year later is over 97%, not over 97%. Let X be the profit made by the insurance company. Find the expected value of the profit. And I'm going to do the same thing. I'm going to make a table. All right, and this is what's going to happen. Say that he dies. Here's what the insurance company will make. He paid in $400, but they have to pay out $10,000. So they're net losing $9,600. Okay, that's what happens if he dies. They lose $9,600. If he lives, they gain $400. They don't give that back. Okay, so this is going to be $400. Now, the chance that he lives is 0.9715. It's hard to do 4 decimals in your head, so take your calculator and do 1 minus 0.9715 to get this number, and you get 0.0285. All right, and I want the expected value, okay, or the mean. Okay, so I want the expected value or the mean. So here's going to be my E of X. I'm going to say negative 9,600 times this plus 400 times the probability there, 0.9715. Pause the video and type it in, and you should get this. And that's an expected gain. And it's an expected gain of $115. On average, because they're going to sell this to many 70-year-old men, on average, they're going to make $115 per person. All right. We will come back to this in a minute because I'm going to show you something on the calculator. So let's skip that, but we will come back. And what I want to talk about is our variance. Variance and standard deviation is a measure of spread just like before. And what the variance is, it's the sum, and you're going to take your actual value minus your expected value, and you're going to square it times your probability. Very similar to what we did before when we were doing, when we did standard deviation and variance by hand. Once you get that, the standard deviation's easy. I just take the square root of the variance. All right, and I want you to look at this one. It's the same problem we did with the computer. Okay, so let's look at this one. And I'm going to show you how to do this by hand, and then I'm going to show you how to do this on the calculator. Here's the same problem that we did a little bit ago, where we found the mean, and we found u of x to be 1.2, the expected number of defective pixels. I'm going to show you how to do the standard deviation by hand. Then I'm going to show you how to do this on the calculator. So here is the standard deviation by hand. We're going to start with the variance. And what I'm going to do is I'm going to take my actual data, 0, minus what I expected, 1.2, square it, times the probability. And I'm getting that from my formula right there. If you look at our formula for the variance. And then I'm going to do plus, and I'm going to go with 1. And I'm going to do 1 minus 1.2 quantity squared times 0.5. And I'm going to do plus, I'm going to start on the next line. I'm going to do plus 2 minus 1.2 squared times 0.2. And then 3 minus 1.2 squared times 0.1. I'm going to tell you that this is not an easy thing to type on the calculator. So I want you to do the best that you can, but if you don't get it typed in correctly, that is fine. All right, so here's how I'm going to type it. I'm going to type 0 minus 1.2 squared times 0.2. And then I'm going to type, and I'm typing it just like it's written. 1 minus 1.2 squared times 0.5. And then I'm going to type 2 minus 1.2 squared times 0.2. And lastly, 3 minus 1.2 squared times 0.1. Push enter. If you got 0.76, that's great. If you didn't, don't try to type it again. It doesn't matter. But my variance is 0.76. So my standard deviation is the square root of the variance. The square root of 0.76. Whoops, sorry. And look what I typed wrong. The square root of 0.76 is this. And I'm going to do 4 decimals. I'm going to say 0.8718. Now, I think that's a difficult thing to type. What I want you to do, I want you to go to your calculator, and I want you to go to statistics. And if you have data in your list, I want you to clear them. We've talked about how to clear the lists. So clear your lists. Notice it takes out everything you have in there. I want you, in the first column, I want you to put the X values, 0, 1, 2, and 3. Now we haven't worried about those frequencies. They've always been 1. This is where our frequencies are going to start to matter. So in the frequency column, I want you to put in your probabilities. Okay? And once you've done those, when you go to stats and you look down this list and you look at your mean, it gives you that expected value, that 1.2. And the population standard deviation, the 0.8718. And sample mean it gives you, I think, because this is a population, I think it gives you sample mean because it doesn't matter, because the mean's the same no matter what. But notice it doesn't give you sample standard deviation because it knows that it is a population when you're doing a probability distribution. Go back to that one that we skipped about the AP tests. And I want you to go back and try that again. So I'm going to go into my data. This will give you practice on the data too. I'm going to clear my table. And I'm going to input my possible scores. So 1, 2, 3, 4, and 5. And then input the frequency. All right, and then we're going to do the same thing. I'm going to go over to statistics. And notice it's going to give you the mean is 2.47. So mu of x is 2.47. And the standard deviation of x is 1.3598. And it gives you the population variance too. Most of the time, they're not going to ask you for that.